I'm now recording a sequence of examples of linear programs. That is, how you take a verbal problem and convert it into a linear program. So here we have this dog food problem where Ruff makes dog food out of chicken and pork. Chicken has so much protein and fat, okay, numbers specified there, and pork also has protein and fat. And then we have a bag of dog food, must contain so much protein and so much fat. Then we have the cost of chicken and pork, and how many ounces of each should Ruff use in each bag of dog food to minimize costs. So we have here what is sometimes called a product mix problem. Now, to start out, every linear program has variables. Now, these are just like variables in an algebra class. You could use x, y, and z, or x sub 1 and x sub 2, or in our case, we'll try to be slightly more clever and use variables which remind us of what they represent. So, for instance, I'm going to use a variable for chicken. I would use c rather than x. If I wanted a variable for pork, I'd use a p for that. Now, a lot of students look at a problem like this and they're not really sure what the variables should be. You know, like they might think, like I just said, well, maybe the variables refer to how much chicken and how much pork. Another student might say, oh, but we also have protein and fat. Which is it? Some of those or all of those? What should our variables be? And I find it very much helps to zoom in on the sentence which is actually stating the question or the problem. And that would be this last sentence here. If chicken costs so much and pork costs so much, how many ounces of each of those should Ruff use to minimize costs? How many ounces of each should we use? What's the word each talking about? It's talking about the chicken and the pork. So that helps us isolate what our variables should be. We'll use a C for chicken and a P for pork. And that will represent the ounces of chicken and of pork. All right, so a linear program can have more than two variables, but this one only has these two. The next ingredient in every linear program is what is known as the objective function. And the objective function is, you might say, sort of the goal or the object of the problem. It's always what we want to maximize or minimize. And when we were looking at that last sentence, it stated that we wanted to minimize our costs. So we'll just say, we'll use abbreviation min for minimize. We want to minimize our cost. And the trick is, we want to convert that into a statement using these variables that we already chose. A good habit to get in is to figure that your objective function will most likely contain both of your variables. So I'm just going to type a C and a P here just to get us started. Now here's what you want to do to create a mathematical statement out of this. We're talking about cost here. Do you have a cost value for chicken? Well, yes, chicken costs 35 cents an ounce. So let's put the 35, let's attach it to the chicken. That'd be 35 cents times the amount of chicken. And by the way, I just inadvertently changed it to $0.35. You could leave it as 35 as long as you kept track of, you didn't forget at the end that you were talking about cents. Most people talk about dollars, which is why I did this little conversion. Similarly with pork, the cost of pork is 25 cents times the number of ounces of pork. So this would be the cost of chicken. The next one would be the cost of pork. And to get the total cost, we'd want to go and add those together. That will be our objective function. Now there's a third ingredient that every linear program will have, and that is what are called constraints. Now constraints represent one of two things. Either requirements or limitations. Now let's scan the problem here. Do we have any requirements? Well, in the middle of the problem there, we're required to have 210 grams of protein and 154 grams of fat. So we will have a constraint for each of those requirements. So I'll come down here, and first off, I like to label them in words. Okay, so there will be a constraint for protein, and then we'll have another separate constraint for fat. So we'll construct those next. Now, just like the objective function, figure that these are likely to have both variables again, the C and the P. And what we want to do is see if we can find the coefficients for C and P. Now, the coefficients will be found by seeing, does chicken contain protein? Does pork contain protein? If so, what are those values? Well, chicken has 10 grams of protein, so its coefficient will be 10. And then pork, let's see, pork has 2 grams of protein, so its coefficient will be 2. So notice I did the same logic I did up here. I was just looking for protein values. And if I put a plus sign between them, that'll be the total protein. Now, with constraints, they won't end just there. You need to indicate either what you are required or what you are limited by. And we see here that a bag of dog food must contain at least 210 grams of protein. We're talking about protein here, so we need to be at least 210. Mathematically, that would say we are greater than or equal to 210. So a constraint will have a left-hand side, it will have an inequality, in some cases maybe even just an equal sign, and on the right-hand side it will have the value you're constrained by. Let's do the same logic for fat. So we will have a C term. Let's see, does chicken have fat? Yes, 5 grams per ounce. So for chicken, the coefficient will be 5. Does pork contain fat? According to this, 15 grams. So we would have as the coefficient there 15 for pork. And the requirement is that we have at least, meaning greater than or equal to, and it says you need to at least 154. So notice the logic in all these statements. Once I've determined my variables, I try to use them in the objective function and also in the constraints. Now, could you have a constraint that wouldn't have both variables? Well, yes. Let me give you an example. Suppose chicken did not have any fat. So we'd look at the fat line here, and let's suppose chicken had no fat. Well, then you'd have a 0C. Well, 0C, you might as well just drop the C out of the picture altogether and it would be absent. But a good idea is to figure it'll be there and then just drop it if for some reason you don't need it. Finally, we do have one more constraint that is an element in almost all linear programs. We can add chicken and we can add pork and we can blend them together in this dog food recipe. But one thing we can't do is we can't put in a negative amount of chicken or a negative amount of pork. The values have to be at least 0. So what we have are what are called non-negativity requirements. My fingers are doing a poor job of spelling here. Okay, non-negativity requirements, and those can simply be written as both the amount of chicken and the amount of pork need to be greater than or equal to 0. Now, at this point, we have finished setting up this linear program. It can be solved by using Excel Solver. What I'd like you to do, if you don't already know that, is go to my video using Excel Solver for linear programs, and you can easily get the answer to this problem.